For our circuit design, we focus on efficient communication protocols to keep wiring simple and response fast. First, the input device. The analog joysticks as our controller, it communicates with the Arduino using analog signals. Inside the joystick are two potentiometers, one for the X axis and one for the Y axis. We connected these pins to A0 and A1. As we move the stick, the voltage changes, and the Arduino reads this as a value between 0 and 1023 to determine Mario's position. Second, the output display. For the visual output, we use an 16 by 2 LCD with an I2C backpack. Instead of using 6 or more wires for parallel communication, the I2C protocol allows us to send all display data using only 2 wires, SDA or serial data and SCL, serial clock, which are connected to the Arduino's A4 and A5 pins. The logic flow and wiring is straightforward. The Arduino reads the analog input from the joystick, processes the game physics in the code, and then sends them graphical updates to the LCD over the I2C bus. For the joystick start button, we connected the switch pin to digital pin 2. Crucially, we utilize the Arduino's internal pull-up resistor in the code. This ensures that the button state remains stable and doesn't float when not pressed, preventing accidental game starts.
Let's walk through the Arduino sketch. First, we handle the communication protocols. We include the wire and liquid crystal I2C-H libraries. These are essential for the PC protocol, allowing the Arduino to communicate with the display using just two data lines at address 0 by 27. We also use byte arrays here to design our custom graphics. By defining these binary patterns, we created the custom characters for Mario and the obstacles.
In the setup function, we initialized the I to the second C for our communication using LCD.init. We also configure our inputs. For the joystick button, we use input _ pull up. This utilizes the Arduino's internal resistor to ensure stable digital reading without needing extra external components. Moving to the main loop, responsiveness is the key. Instead of using the standard delay function, which poses the whole system, we use millis. This creates a non-blocking timer. It compares current millis against previous millis. This allows the game to move the obstacle at a setup speed while simultaneously listening for a player inputs instantly. This prevents the controls from feeling laggy.
For the logic, we use if-else statement to process the analog input. We read the joystick using analog read close open parentheses. If the value crosses our threshold of 800, the logic registers a jump and changes the Mario row value to 0. We also added a gravity timer here to limit how long the player can stay in the air. Finally, handling the display output via I2C can be slow. To fix flickering, we implemented a state change logic using a flag called showDraw. The code only sent a data over the I2C bus to update the screen if the character or enemy actually moved. This minimizes communication traffic and keeps the graphic shapes.
Ano, may limit. Hindi, hindi pwedeng habang buhay nasa taas. Ano yan?
Okay na?
Hindi. Saan?
For the challenges section, we face a major hardware scare. During our initial testing, both the LCD display and the joystick were completely unresponsive. We initially panicked, thinking that our 12C module or joystick sensor were defective or burned out. However, after troubleshooting with a multimeter, we discovered the real culprit: faulty female-to-male jumper wires. The internal connections were broken, causing the signals to fail. The solution: to eliminate the bad wires entirely, we came up with a hardware modification. We carefully bent the pins of 12C LCD backpack. This allowed us to plug the LCD directly into the breadboard, creating a solid, stable connection without relying on the faulty cables. Once we did this, the game worked perfectly.